Okay, so this is the sample problems for percent yield. Now, the main formula for percent yield is that percent yield is always equal to the actual yield divided by the theoretical yield. Now, for each problem, you will always have to figure out, using stoichiometry, the theoretical yield. However, some problems give you the actual yield and ask you to solve for the percent, whereas others give you the percent and ask you to solve for the actual. Oh yes, it's also times 100. So, depending on which type you have, you're going to be either solving for the percent or solving for the actual yield. But you always use stoichiometry in order to find the theoretical yield. So, in our first problem, it reads, methanol can be produced by the reaction between carbon monoxide and hydrogen. If 8.60 times 10 to the third grams of hydrogen is reacted with plenty of carbon monoxide, and 3.57 times 10 to the fourth grams of methanol is produced, what is the percent yield of this reaction? So, since this question asks for the percent yield, we know that they give us the actual yield. And since yield means product, the fact that they give us the amount of a product means that this is the actual yield. So, we know that actual yield, 3.57 times 10 to the fourth grams of methanol divided by the theoretical yield times 100 will equal the percent. We now need to calculate the theoretical yield using stoichiometry. Now, first step with all stoichiometry problems is to balance the chemical equation. This one is simple, so we just simply put a 2 in front of the hydrogen, and that balances the equation. Step 2, we set up our starting point and end points. Our starting point is right here. It's the amount of a reactant. In percent yield questions, the amount of reactant given is always the starting point. So we have 8.60 times 10 to the third grams of hydrogen, and the question is, how much product is being formed? Now the endpoint, units, and identity must be the same as those of the actual yield. Since they tell us that a certain number of grams of methanol are actually produced, we now need to calculate how many grams of methanol were theoretically supposed to be produced. So that becomes our endpoint. We now do a mass-to-mass stoichiometry. First equality is always the mole ratio. In this, we have 2 moles of hydrogen are going to be equivalent or equal to 1 mole of methanol. The coefficient in moles of our starting point equal to the coefficient in moles of our end point. We now look at the units of our starting point and end point. Since that is grams, we need to have the molar mass of hydrogen. 1 mole of hydrogen gas, H2, is equal to 2.02 grams of hydrogen gas. We also now need to have, since that's grams, we need to have the molar mass of methanol. Well, figuring that out over here, where we have some space, we have 1 carbon, we have 4 hydrogens, and we have 1 oxygen. So those are times the average atomic mass, 1.01 and 16. So we have 12.01, 4.04, and 16. We add it up and we get 32.05. So we know that 1 mole of methanol is equal to 32.05 grams of methanol. Now that we have that, we can set up our grid. So we have 8.60 times 10 to the third grams as our starting point, which always goes in the top left-hand cell of the grid. We use, since we have grams of hydrogen there, we want grams of hydrogen there. So that's 2.02 grams of hydrogen, and it's equal to 1 mole of hydrogen. Cross that out, draw another vertical line. Now we have moles of hydrogen on top. We want moles of hydrogen on the bottom, right there. So that's 2 moles of hydrogen, and it's equal to 1 mole of methanol. Cross that out. And finally, we have moles of methanol here, so we want that down here. 1 mole of methanol is equal to 32.05 grams of methanol. Using our calculator, numbers on top we multiply, numbers on the bottom we divide. So we have 8.60 EE 3. It's on the bottom, so we divided by 2.02 divided by 2 times 32.05 equals. Now we want this in scientific notation and in correct number significant figures. So we have 3 significant figures in our starting point. So we want to have 3 significant figures in our answer. So we have 6.82 times 10 to the 4th grams of methanol. Now this is the amount that theoretically should have been produced. So that is our theoretical yield. That number needs to go here since theoretical yield goes on the bottom. So that's 6.82 times 10 to the 4th grams of methanol. So now we do another calculation where we take 3.57 EE4 divided by 6.82 EE4 times 100 equals, and since these numbers go out to 3 places past the decimal, since these numbers have 3 significant figures, we round the answer off to having 3 significant figures, and the answer becomes 52.3, and we add percent as our unit. So that is the first type, where they give us the actual yield and we calculate the percent. Now in this problem, it's going to be slightly different. This problem shows us that titanium 4 oxide is a white compound used as a coloring pigment. Solid titanium 4 oxide can be prepared by reacting gaseous titanium 4 chloride with oxygen gas. A second product of this reaction is chlorine gas. So here is our unbalanced equation. To balance it, since we have 4 chlorines on the left, we simply put a 2 here, and now it is balanced. Now, the question itself reads, if 6.71 times 10 to the 3rd grams of titanium 4 chloride reacts with plenty of oxygen in a reaction that is 75% efficient, how much titanium 4 oxide could actually be expected to be produced? Now, in this reaction, again, this is a percent yield. Percent yield is equal to actual yield divided by theoretical yield times 100%. Since they give us the percent, and since we always calculate the theoretical yield, This problem, we are going to be looking for the actual yield. So, to rearrange this formula so that it gives us the actual yield, I multiply both sides by the theoretical yield and divide both sides by 100. The hundreds cancel out, theoretical cancel out, so actual yield is equal to the theoretical yield divided by 100 times the percent. So in this question, we have the theoretical yield needs to be calculated, but we have the percent yield. So we're going to take whatever the theoretical yield is, divide it by 100, and then times it by the 75%. And that should give us our actual yield. So now we need to do a mass-to-mass stoichiometry. The amount that they give us is a reactant. So that is our starting point. 6.71 times 10 to the third grams of titanium 4 chloride. And since they're asking for how much TiO2 could actually be expected to be produced, that is going to be our unknown. Since we're dealing with masses here, that's how many grams titanium 4 oxide could be produced. So we go ahead and set up our problem by looking at our equalities. First of all, we need the mole ratio. The identity of our starting point is titanium 4 chloride. Coefficient in front of that is a 1. So for our mole ratio, we have 1 mole of titanium 4 chloride is equal to our endpoint is titanium 4 oxide, which also has a 1. So that is 1 mole of titanium 4 oxide. Now we need the molar masses. Because this is grams, we need the molar mass of titanium 4 chloride. And because that is grams, we also need the molar mass of titanium 4 oxide. So off to the side here, I'm going to go and say, all right, we have titanium and chlorine, 1 and 4. Titanium's molar mass is 47.87. Chlorine's is 35.45. So we have titanium at 47.87. Chlorine is 35.45. We multiply that out, and we get 4 times 35.45 plus 47.87. We get total 189.67. Once again, this is 141.80. That's 47.87. And then we add it up. So we have 1 mole of titanium 4 chloride is equal to 189.67 grams of titanium 4 chloride. Now we want to do the same thing again. We need the molar mass of titanium oxide, or titanium 4 oxide. So again, we have titanium, now oxygen. We have 1 and 2. That's still 47.87. Oxygen is 16. 2 times 16 is 32. And we have 79.87 is our molar mass for titanium 4 oxide. So we write out 1 mole of titanium 4 oxide is equal to 79.87 grams of titanium 4 oxide. And now we set up our grid. 6.71 times 10 to the third grams titanium 4 chloride. We have grams of titanium 4 chloride, so we want grams of titanium 4 chloride. They're right there. 189.67 grams of titanium 4 chloride is equal to 1 mole of titanium 4 chloride. Cross that out so we don't use that again. Another vertical line, we have moles of titanium 4 chloride. So we get those right there. It's a 1-to-1 ratio, so 1 mole of titanium 4 chloride equals 1 mole of titanium 4 oxide. And now we have one more equality, so one more vertical line. We have moles of titanium 4 chloride right there. So we put 1 mole of titanium 4 chloride is equal to 79.87 grams of titanium 4 chloride. So on our calculators, we go ahead and take 6.71 EE3 divided by 189.67 and then times 79.87 equals. We have 3 significant figures in our starting point, so our ending point will be 2.83. Again, since the decimal moves more than 2 places, it must be in scientific notation. 2.83 times 10 to the third grams titanium 4 oxide. And once again, that represents the actual yield. The theoretical yield, my mistake. That's the theoretical yield. And that, therefore, goes there. So we put in 2.83 times 10 to the third. All right. So we go ahead and on our calculator, we take 2.83 EE3 divided by 100 times 75 equals. And since that has only 2 significant figures, our answer can only have 2 significant figures. It also must be in scientific notation, since the decimal point would move more than 2 places. So the answer is 2.1 times 10 to the third grams of titanium oxide. And that is our final answer.